All right, so last time we were basically introduced to radiation shields. I'll solve a problem with shields and then talk about reradiating surfaces. So this is where we were last time. We had this problem. We had two very large parallel plates that were gray and diffuse surfaces. So the top plate, surface 1, the bottom plate, surface 2. And the top plate was black because of the emissivity equal to 1. The bottom plate was not black, it's 0.8. So we built a radiative network with the EB nodes on the two surfaces and only a J2 node, radiosity node for the bottom surface. The J1 node, because 1 minus epsilon over epsilon A is the surface resistance, is equal to 0, it collapses, and so J1 is equal to EB1. We can compute a numeric value for the black body emissive fluxes EB1 and EB2 because they're simply Stefan-Boltzmann constant times t to the fourth power. There's the numeric value for EB1. There's the numeric value for EB2. Take a quick glance again, if maybe I emphasize this, but compare those two numbers. Somebody says, I'd like to give you a gift. I'll give you $115,600 or I'll give you $1,452. I know that's a great gift. I would take either of them, but which one would you take if you had the choice of either one? There's a huge difference between these two numbers, is there not? But is there such a huge difference between the temperatures of 1200 and 400? Not really. I mean, it's only a factor of 3 to go from there to there, true? Is there a factor of 3 if I just take 1500 multiplied by 3? Do I get... No, not at all. That's the power of the t to the fourth. You almost have to see it in action to say, that number, did I run this correctly? Are these two numbers that much different? It's the temperature to the fourth power in that Stefan-Boltzmann law that makes the high temperature so much greater black body emissive flux. All right. So then we have two resistors in our network, the geometrical and the surface resistance. We were asked to calculate the net radiation exchange per unit area. Right, Q is equal to just a resistor flow network problem. That area, bring outside, right here. This is the same area. Bring it outside and divide Q over area so you get a flux. And then you see that this 1 over F just turns into 1, and 1 minus epsilon over epsilon turns into 0.25. So the most of the resistance to heat transfer is just in the geometrical resistance. And 20% is in the surface resistance. But the overall flux, 92,900. Then we were asked, what is the radiosity, J1, for the top surface or plate? And we talked about that being the same as EB1. Hence, it's 115,600 watts per meter squared. And then what's the irradiation for the top plate? We talked about 3 ways of calculating G. And the easiest one is just go ahead and get J2, and then J2 is equal. What comes out of surface 2 is going to impinge only on surface 1. So for this problem, that's pretty easy. And then how do I get J2? Well, J2 would be a flow of this Q from this node to that node through that last resistor. And so just saying through that last resistor, the surface resistance, you get J2 is equal to EB2 plus Q times the resistance surface. Boom. And there it is. There's G1. Then I asked the question. This is where I think we left off. How can we reduce the rate of heat transfer? Introduce a shield, a radiant shield. So if we introduce a radiant shield for this problem, all we do is have our physical surface top, physical surface bottom, a radiant shield. Let's build an equivalent network. We'll have the EB1 surface, or node, sorry. We come off with a resistance 1 over FA, or AF. Then we get to the J. But I need to really be careful here. We introduce surface 1. That's surface 2, surface 3, and surface 4. So the foil the radiant shield has two surfaces, two sides to it. So don't forget that there's surface 2 and surface 3 for that shield. So this is the J2. Then you'll have the EB2. We talked, I think, last time that EB2 is equal to sigma T2 to the 4th. True? And then I asked, is there an EB3 or not? There's not. And that's a tricky part right there, because it has the same numeric value as the EB2, hence they're the same temperature, they're the same black body emissive flux. I know one is going up, one is going down, but it's the same. So we come off to J3, then we have the resistance to J4, then the resistance to EB4. So this is a surface resistance, 1 minus epsilon 4 over epsilon 4A. This is a geometrical resistance, 1 over area 4 to 3 or 3 to 4, A3, F 3 to 4. This is a surface resistance, 1 minus epsilon of the foil over epsilon of the foil area. This is the same value of R sub S, same 1 minus epsilon of the foil over epsilon of the foil A. And this is the geometrical resistance, 1 over AF. A1, F1 to 2 is good enough. Okay. So now what is the net radiation exchange per unit area between the plates? Would it be that Q double prime is equal to EB1 minus EB2 divided by the sum of the R's? That little pesky area, what I do is I want, this is correct without the area, but if I divide by the area and multiply by the area, then it's fine, right? And so if I take a look at what is the area times R sub G for this first resistor, isn't that just 1 over F? Isn't that just 1? Okay. And then for this next resistor, the area times resistance surface. Okay, well, what's my emissivity of this surface? 1 minus 0.2 divided by 0.2. That's 4. This will have the same value of 4. This will have the same value of 1. This will have a value of 0.25. We calculated that before. The 1 minus 0.8 divided by 0.8, 0.25. So when we sum, the sum of the R's times A is equal to, you have 1, 4, 4, 1, and 0.25. The sum is equal to 10.25? Is that right? I didn't want to do that too fast, but so what we have is we have the same black body emissive potential for surface 1, which was 1200 Kelvin, which is, looking at my notes, 115,600 minus the 1, what is it for the bottom? 1,452. Both of those are watts per meter squared. You divide it by 10.25, and the flux for the new problem with the shield with the emissivity of 0.2 is 11,330 watts per meter squared. 11.3 kilowatts per meter squared. What was it before? What was it before? Wasn't it 92,900 watts per meter squared? Introducing just one little foil with the emissivity of 0.2 on both sides of it dropped the Q double prime, dropped the radiant heat transfer. That is a radiant shield. It's effectively resistor, additional resistance. All right. What about the radiosity for the top plate? What about J? What is it? The J of the top plate, J1. This is a number 2 right there, J2. What is J1? EB1 It's the same value as before. It's 115,600 watts per meter squared. No change. What about the irradiation for the top plate? What about the G? The G1. Is that still going to be J2? Yeah, it will be for this problem. And can I solve for J2 maybe using the flow through this resistor from the EB1 to J2? And so is J2 equal to EB1 minus Q double prime times R sub G? Does that make sense? And so if you calculate the J2, that's going to give you a value of 106,200 watts per meter squared, which is the same as G2, or G1, sorry. Well, what was G1 previously? G1 previously was 24,700. Did it go up or down? What's that foil doing is it's reflecting more of the radiation back to the top surface. And that's why it's reducing the overall rate of heat transfer. You see that? So G went up. G1 went up. These questions aren't easy, are they? Here's 3 additional questions. What is the radiosity for the bottom plate? Well, the bottom plate was numbered 4. So what are they asking me to solve for? What symbol do I want to use? And what are the SI units for it? J4 in watts per meter squared. So how about the irradiation for the bottom plate? What is that? Isn't that G4? And then what is the temperature of the foil? The temperature of the foil. So can I take a break and watch and see how you do on this? So I'll give you a couple seconds, organize your thoughts. I'll walk around the room and see. How would you solve for J4? How would you solve for G4? How would you solve for the temperature of the foil? Okay, so we go through that network and we have J4 right here, and then we have EB4 right there, and then we have a resistor that's a surface resistance, 1 minus epsilon 4 over epsilon 4A. Okay, and we do know that the Q is coming through it. All right, so we can get that the equation. Let me write it up here. That Q is equal to J4 minus EB4 divided by the resistance. True or false? And that is our surface resistance. Just to chase units, this resistance, if you leave the area in it, has units 1 over meter squared. And then this Q, without the Q double prime, has units of watts. And the units of both J and EB are watts per meter squared. Make sense? The units are going to work like that. So I think I wrote something incorrectly over here. Did I? Yeah, I needed to leave that out. Sorry about that. My error. My mistake. Okay, so let's run over here. So now, if I want to calculate J4, it's equal to EB4 plus Q times R sub S. And you said, but we calculated Q per unit area. Fine, then put an area, then I have the area times R sub S, and I had the flux. Okay, so substituting numbers, EB4, 1,452 watts per meter squared. What was our flux through the plate when we had a radiant shield emissivity 0.2? it was 11,330 watts per meter squared. And then the resistor times the area, the A times the R sub S is 1 minus epsilon over epsilon, which is 0.25. 0.25. Dimensionless. And so J4 comes in at 4,284 watts per meter squared. How about the irradiation for the bottom plate? How would you solve for G4? Get J3, and you know that's equal to G4. And all you do is back it up. And here's the J3 node. There's an additional resistor, 1 over AF. And so your equation for J3 is going to be E, just kind of looking from here to here, is saying EB4 plus Q double prime times area resistance surface plus area resistance geometrical. This is the 0.25, this is the 1. And so we calculate J3, which is is G4. And we find that G4 is 15610 watts per meter squared. How about the temperature of the foil? How are you going to calculate the temperature of the foil? Get EB2. And so guess what? You just kind of back up to this node, EB2. What was this? This is the resistance of the surface, 1 minus epsilon of the foil over epsilon of foil area. Same type of equation. To get EB2 is equal to the 14, well, let me write it out symbolically. EB4 plus Q double prime times A R sub S4 plus A times resistance geometrical plus A times resistance of foil surface resistance on the foil. Does have different emissivities in this surface resistor here and that surface resistor. And so this becomes 0.25, then you add 1, then you add 4. And so we find that EB2 comes in, I'm running out of room, sorry about that. EB2 is 6928 watts per meter squared. How does that help me get T of the foil? That's right. So this EB2 is equal to sigma temperature of the foil to the 4th power. Temperature of the foil is EB2 divided by sigma to the 1/4 power. Now, if you run a calculation and the foil temperature is greater than 1200 or less than 400, what do you suspect? Error. And so the foil temperature for this problem, temperature of the foil, comes in at 1,000, I think I'm looking at it here, 18 Kelvin. 1,018 Kelvin. Is it closer to the top surface temperature or closer to the bottom surface temperature? Closer to the top. So it has a strong black body emissive flux associated with it. You ready for some clicker questions? Let's try this one. If the emissivity of the foil is changed from 0.2 to 0.4, what are we doing? We're increasing the emissivity. This is the problem we just solved, 0.2. We're making it 0.4 for the emissivity of the foil. The net radiation exchange between the plates Q double prime was 11,330 watts per meter squared. What will it be now? And I'll give you time to answer that. Will it increase above that value? Will it remain essentially the same, or will it decrease? How is the emissivity of the foil affect Q double prime? All right, so this one was with the emissivity of 0.2, but when you move to an emissivity of 0.4, it's getting more black, but you don't want a radiant shield to be black, do you? You would like a low emissivity. If you look at a lot of those resistances, 1 minus epsilon over epsilon A of that foil, that was, you had two of those for the top and bottom surface, and they were much greater than the bottom surface's resistance, not geometrical, surface resistance. So you would expect that this will increase, that it actually goes up to 22,120 watts per meter squared when you change the emissivity. Make sense? If you want to put in a better radiant shield, put in a low emissivity shield. So, increase. Let's just grade this. Make sense? All right, you want another one? Might as well, right? So, same thing, change the emissivity of the foil. What happens to the radiosity of the top of the foil? So we had, what number did we use for the top of the foil? Wasn't that J2? So J2 is 106,000 watts per meter squared. What is the new radiosity of the top of the foil if you change the emissivity? Oh, polling stopped, right? Did I start it even?
Yeah.
It stopped? Okay, well, let's take a look at it. Well, we're guessing. It's not an easy problem. It's really a hard problem. But let's take a look at it. It goes to 95,450 watts per meter squared. Let's try another question. The emissivity of the foil is changed, same game. What happens to the radiosity of the bottom plate? And let me help you with this one a little bit. Think about at the end of that network. What do we have right here? EB4, and then we have J4, true? And this is 1 minus epsilon over epsilon A. And what's coming through there? Q. So for this problem, did EB4 change? No change. Did the emissivity of the bottom plate change? No change. Did Q change? Yes. What happened to Q? It went up, right? This is the first question. It went up. So if you have more flow, what happens to the difference between EB4 and J4? Doesn't it become further apart? Doesn't J4 become greater than, larger than it had been? So what does J4 do? It increases. Okay, we're still guessing, but that's okay. What's the numeric value for J4 for the new one is 6,981 watts per meter squared. All right. Can you use this type of logic that we used on this last question, and now we'll rerun this question right here. We'll re-ask, forget it, I already gave you the answer. The way to actually calculate or answer this question about the radiosity of the top of the foil is to do a little resistor network. Okay, and what you have here is you're going to have you can start from the bottom or you can start from the top. EB1, which is J1, right? Then it comes down to J2. There's one resistance, 1 over AF. Okay, and we're going to now have the Q goes up, but there's no change for the EB1, no change for that resistor. What happens to J2? It's further away. It's a larger delta, a larger difference in the potential, hence J2 goes down. And I showed you the numeric value. It's J2 is 95, whoops, that's a bad looking 95. 95, 450 or 460 watts per meter squared. All right. Well, we also want to talk about reradiating surfaces. So this is especially if you have a 3-surface enclosure. And what do you think is particularly, unique about a reradiating surface? All that comes in goes out. If all the radiant energy that comes in goes out, what about the net transfer with conduction on the backside, or heat source or heat sink on the backside? Zero. So there's no external flow in or out at that surface. It's like back of it's insulated. Well, let's solve a problem that requires us to analyze a reradiating surface. We have a metal plate with a coating that's been put on it, and it's now needing to be cured, and you place it 0.5 meters below an electrically heated surface. Both the cured plate and the heated surface are the same rectangular dimension of 1 meter by 2 meters, and they're aligned with each other. So you have the plate that maybe is heated, and then below it, aligned, is another plate that is going to be cured. The two are in the large surroundings maintained at 300 Kelvin. And the heater is well insulated on the top side, so only the bottom face of the heater, which is radiating down to the plate that's being cured below it, that's the only one which is radiating energy. Both surfaces can be treated as black bodies. That may simplify the resistors. There's no 1 minus epsilon over epsilon A. And the heated surface is maintained at 700 Kelvin because of electric heating. Think about electric heating like that. Convection effects are negligible. Calculate the electric power required to operate the heater. So what do? Is we say, I'm interested in calculating the symbol Q supplied to the heater in units of watts. And then for part B, I need to calculate the temperature of the cured plate, temperature of this cured plate, P, or some symbol like that, in units of Kelvin. Okay, make a radiative network. So we're going to have a node. It'll be EB1 for what surface? The bottom side surface 1 of that plate that's radiating. The top surface of the plate that's being cured is surface 2. The bottom side of the plate that's being cured is surface 3, and the surroundings is surface 4. So if we have our network, we have EB1, then we're going to have, let's say, EB2, and we'll have over here EB4. And do I have another node for EB3? They don't give us the thickness of the plate, but what type of plate is it? Metallic, okay. So do you think there will be a significant temperature gradient across that plate? No. Let's assume it's not. They have no information to tell us that it'll be. So it's an isothermal plate. It's an isothermal plate. If it's isothermal, EB3 is equal to EB2. So just collapse them. So I really only have 3 EB nodes. Now, how does the radiant energy flow from the top plate to the bottom plate? We have a resistor, 1 over AF. It's a geometrical resistance, black body exchange. Then it can also flow 1 over AF. But here, this is area 1, F1 to 2. This is area 1, F1 to 4. See, some of the photons can go and directly hit the plate that's trying to be cured, or they could go and hit the surroundings. All right. Then think about plate 2. You have the top of plate 2. You could have it going back to EB1. That's included in that resistor already. Or you could have 1 over area 2, view factor 2 to 4. True? There's one other resistor. It's associated with the bottom surface of the cured plate. It's like this. It's 1 over area 3, view factor 3 to 4. Can you see that? The bottom of the plate is seeing completely the surroundings. All right. Now, if this is the network like that, we're going to have to calculate the areas and the view factors. The areas are real simple. What's area 1? That's 1 by 2. That's 2 meters squared. Area 2, 2 meters squared. We really don't need, well, area 3 is also that same. Oops. They're all 2 meters squared, 2 meters squared, 2 meters squared. We really don't need the large surroundings area. Area 4 is just large. So area 4 just much, much greater than area 1. Because on the view factor calculations, we just go from the surface areas we know to the large surroundings. Okay. What about the view factor? We need it 1 to 2. We need it 1 to 4. We need it 2 to 4. We need it 3 to 4. Which of these view factors can you tell me about? Okay. Is 2 to 4 equal to 1 to 4? Same size plate, symmetrical. So if 1 to 4 is the same as 2 to 4? Yeah. So that helps. And what about 3 to 4? It's 100%. 1. All right, now how do I get the view factor from, let's say, surface 1 to the surface 2? Well, you go and get some help. And people have tabulated them and put them into equations or into figures before. So what we have is we have a line, parallel rectangles. That's the illustration right here. And so top to bottom or bottom to top, it doesn't matter. And for this dimension, maybe that's 2, maybe this dimension's 1, and this dimension L. What was L? 0.5 meter? 0.5? So you just calculate x over L. That's 2 over 1/2. That's 4. So there's 4 somewhere along this line. And then you calculate y over L. Y is 1 over 1/2. That's 2 somewhere along this line. Where they intersect, and you just read off, and it's slightly over 1/2. So for that orientation and separation and size of plates, basically the view factor is 1/2. You say, I think we can do better. Well, here is the view factor given in equation form for this problem. And here it is implemented in Excel. And I make it look easy. It took me more time to debug it because it's a little bit on the it's tedious. But when you compute it, you can see that Excel coughed out implementing that equation a view factor 0.50899. There you go, close enough. So 0.509 would be good to 3 significant digits. Well, it's radiant heat transfer. It's good enough if you just 0.5, right? But let's go back to our calculations. So 0.509. What about 1 to 4? So if what's 1 to 4 if 1 to 2 is 0.509? 194. Isn't it 0.491? All right. So you have your view factors. Now what do you do to solve? Do we know EB1? That's sigma T1 to the 4th. Do we know that it's 700 Kelvin? Sure. We know we can calculate a numeric value for that. How about EB4? Well, it was 300 Kelvin for the surroundings, so it's sigma T surroundings to the 4th. So we know the values of these two potentials. True? So the heater is supplying Q, and it can come out of that network either this place or that place in the surroundings. But what about this cured plate? The cured plate acts as it's no sink or source to change its temperature. So this Q right here is equal to 0. Do you see that at steady state? Yeah, there's a little transient when it heats up or cools down, but at steady state, it's radiating, it's holding there. So this is 0. And so what comes in goes out right there, 100%. So what do I need to do? I just have a resistor network. I just have to think back to electric circuits. And with electric circuits, I need to collapse this into an equivalent network. These two resistors, do it in steps. Going from this node to that node, how would I combine them into a resistor? They're parallel. And then once I have this one, how do I combine this one with that equivalent? Series. And then how do I combine that one with that one? Parallel again. So this is really going to make you good at combining parallel and series and parallel. Compare your resistors. Can you get that equivalent resistance? Sure. So you have your areas and your view factors. Now it's combining, and so what you get is Q is equal to EB1 minus EB2 divided by R equivalent for the whole network. All right. What about the temperature of the cured plate? Once I calculate Q, how do I get the temperature of the cured plate? I really need to get EB2, don't I? If I could get EB2, then I can get the temperature of the plate. Remember that EB2 is equal to sigma temperature of the cured plate to the 4th? Okay, so now the game is to get EB2. How do I get EB2? What is the Q that goes between 1 to 4 in that path, and then what goes in this path, right? If I could find the flow that goes in this path right here, right? How many watts go there? Couldn't I then just use the resistor concept and say that let's call this Q1 to 2. Do this. Is Q that comes in, the answer for part A, equal to what goes directly through that resistor 1 to 4 plus what goes in the resistor from 1 to 2? It's Kirchhoff's current law around the node right here. True? So could I calculate this one? Sure, because I know both of the voltages and I know it's the resistance of that one resistor. I can calculate Q1 to 4 is equal to EB1 minus EB4 divided by the resistance, the geometrical resistance 1 to 4. It's 1 over A1 F1 to 2. So I can calculate Q1 to 2 as Q minus Q1 to 4. And once I have Q1 to 2, you can get that EB2, I'm running out of places to write, EB2 is equal to EB1. Is it going to be plus or minus? Is it going to be higher or lower? It'll be a minus a Q1 1 to 2, that's a bad looking Q. Ah, come on now. Minus Q 1 to 2 times the resistance 1 to 2. Does that make sense? Look good? All right, well, thank you very much for your attention.